Sorry, sir. Still, we are dealing with some issues with audio, so we are trying to resolve it as soon as possible. Sorry for
Okay,
technical issues. Sorry.
no problems. Hello, Professor Brukner. Can you hear me?
Yes, I can hear you, yeah?
It's really sorry.
No problems.
I'm really sorry. I apologize for the delay due to technical problems. We're extremely happy to have Professor Caslav Brukner as our speaker today. This is part of a celebration of the International Year of Quantum. And let me now say a few words about Professor Brukner. He's the scientific director of the Institute for Quantum Optics and Quantum Information at Vienna, and this is part of the Austrian Academy of Sciences. Professor Brukner has received his education at the University of Vienna and the Vienna University of Technology. He has held appointments at many places, including the University of Innsbruck, University of Vienna, Imperial College, and the University of Belgrade. His research interests are broadly in quantum information, quantum foundation, quantum non-locality, and quantum gravitational effects. His work has received many accolades, including a recent award, that is the Paul Ehrenfest Best Paper Award for Quantum Foundation. I would now like to request Professor Brukner to deliver his lecture.
Thank you very much for this nice introduction, and good afternoon, everybody. It's still a morning here in Vienna, but we are awake and happy to discuss some physics. So I will share my slides now. I hope you will gonna see them well. I decided today to talk about an object of investigation that is in the focus of our research already for some time. We call this quantum reference frames. This is a little bit at the edge of, I guess, the series of your presentations devoted to mostly quantum information topics, but it does use quantum information tools to maybe help us understand situations that are not yet fully understood, and also help us understand something about resources that we usually use in quantum information. So it's an introductory talk, and I call it what is an observable in quantum reference frames, somewhat broadly, just to be able to give you some short introduction in this topic, why we think it's interesting, and give you some examples that are maybe interesting also for the people traditionally in quantum information science. So when we talk about physical systems, we usually divide them roughly in two categories. We talk about systems under investigation. I draw here these three atoms, but we have also all kind of usually classical devices in our laboratories, like rods and clocks, which serve as a reference frame, such that we can make some statement about, well, the particle was found at certain position relative to our origin of reference frame in the laboratory, or we performed a measurement at certain time relative to the time reference frame. But certainly, if we think that quantum mechanics is a universal fundamental theory, this division appears a little bit artificial, or rather forced by practical means. But in a certain sense, we believe that all systems, including those that serve as a reference frame, are, after all, of quantum mechanical origin. So in a certain sense, we should consider even quantum reference frames, rods and clocks, at least in some situations, as a quantum reference frames, namely as systems that, like other systems, can be in superposition or entangled with some other system. And that's the idea of quantum reference frames. The idea is that maybe we will learn something more about the symmetry of our laws, or maybe it will help us to understand better some situations if we assume that even the reference frame behave quantum mechanical. And so that's the context of my talk. I will remind you on the notion of the invariant observable. And then I will talk about invariant observable on the classical reference frame, CRF. Then moving to the invariance under quantum reference frames, and then give two examples where I pick up them. There are more, of course, in the literature, but two examples that I feel will provide examples of a usefulness of quantum reference frames as a notion. So let's start with the notion of invariant observables. When we usually perform any experiment, any statement in physics relative to a reference frame. But sometimes some of the reference frames are missing. So for example, if we don't have a well-defined origin for translational degrees of freedom, then only the relational observables, namely the relative distance, have a physical meaning. So we may say this: in the absence of external reference frames for the measurement of an observable, only relational observables are physically meaningful. So these relational observables are then invariant under certain symmetry transformation of some group. For example, if we have some group of symmetry whose unitary representation is UG, then we will call observable to be G invariant if this observable preserve its form under this unitary transformation that represents an element of the symmetry group. So here is an example. In a theory which is Euclidean in translation invariant, this relative invariant observable is the relative distance. So only what matters is really the difference between the ends of this measure length, but the origin or the notion of an x1 position of one end or position the other end are just gauges, are not physical. And we can move reference frame from another to another, at least in our thoughts, without having any changes in physics or without any change in understanding what the relational observable is. Of course, it's not the only relational observable. We can have any functional, which is a function of a relative distance. This would be also an observable. Now, if the symmetry changes, and we know that when we go into the higher velocities, Euclidean theory is not valid. So if the symmetry changes, then also the invariant observables change. So for example, in a Lorentz invariant theory, this x1 minus x2 is not invariant observable. You can still measure it, but what we will get then will depend on the reference frame of Lorentz frame. If we are searching for an invariant observable under a Lorentz transformation or Lorentz boost, then we need to adapt invariant observable in something which we have here, and it's a specific very combination of relative distances in space and time. Now, let's look at the first and the most simple example. I have here two systems represented by these two balls, and the Hamiltonian of this system is a kinetic part plus some potential that depends on the relative distance between these two. So it is a Newtonian two-body system, translation invariant. Now, what we will do in the next slides, we will extend this idea here that I will present now in classical physics to the quantum case. Namely, sometimes I will colloquially say, let's jump on the reference frame of the first particle or a first ball. So if first ball is used as an origin or reference frame, what we usually say, we just move the coordinates from the original one to the new coordinates, shifted by the distance a between the old and new original reference frames. However, if we do so, the Hamiltonian of the systems would be the same. So we really have here even the symmetry of dynamical laws, because no matter where we choose the original reference frame, the physics will remain the same, not only observables, but also the dynamical laws. So we can think about something like invariance of the dynamical law on the reference frame, or coordinate transformation. If we want to go into some field theoretical picture, then we don't have rigid reference frames, so we have to extend this to the coordinate transformations. I will not talk about that, but the spirit is the same, that the dynamical laws governed by the Hamiltonian in this symmetric case remain always the same. Now I move to what quantum mechanics, but only partially on my way to even quantized reference frame. Here I have a particle B, which is a quantum particle in some state phi b. And here I have two possible reference frames, a C and A. And usually when we want to move from description relative from one to another reference frame, what we apply is just that apply some shift operator that generates translations by the generator of translation, which is a momentum on B, with some parameter here. So XA is a distance between the new and the old reference frame. These upper indices reflect from which reference frame I look the particle. So the two origins are at the distance XA, and that's the transformation that I apply. Now I finally come to the idea that was born in this 2019 paper, when we think about three systems, and we will always think that we sit in one reference frame. We do not describe this reference frame because we are within this reference frame, but everything external to this reference frame will be quantum mechanical particles. Now, some of them may be very narrow wave packets, very massive systems, like maybe, again, position of some massive object that we can use as a reference frame, but it doesn't need necessarily to be so. And so then we will think about situations when we sit on some reference frame and we explain everything externally to this reference frame, for example, with some product states where the first particle is very much narrowed. And then we will move into the new reference frame, maybe on this very localized massive particle A, from which we will observe both the old reference frame and still the quantum particle that we had before. And now the situation, how we move from one to another state, even if we make this extension and writes here cats assigned to the old and new reference frame, is not very different from what I just said, because we pick up all these reference frames very narrowed around their classical-like states. However, if we want to go and want to formalize how we do that, we will see that what we actually do is that we perform some reference frame transformation that is a little bit, that reminds on us from the last part. But you see that this X here is the amount for which we will push particle B, is not anymore a classical parameter, but because we have integral of X, it becomes an operator. So what this transformation says is, you see, here's a bra A. We learn out where A is. It could be very well localized, but need not. Then depending on how A is, we push B for the amount X. And then the last part is just swapping between A and C reference frames. And now, if we go into more interesting cases, we may even start with situation which is on the left upper corner, where the reference frame onto which we want to jump really quantum mechanically non-local. So you have a superposition of two peaks. And when you apply this transformation, you will jump on a reference frame, where the old reference frame and your particle will become entangled. You will become entangled, but the relative distance between A and C and A and B will be the same. So here is the relative distance, this one, if A is on the left-hand side, or this one if it is on the right-hand side. So these two relative distance corresponds to these two peaks of the blue peaks of the C with respect to A. So we see that there is some kind of preservation of the relative distance. However, the states that we get from moving from one to another reference frames are very much different. Now this brings me to idea of invariance under quantum reference frame transformation, and I again have the same opening sentence like in a classical case. In the absence of an external reference frame for the measurement of an observable, only relational observables are physically meaningful. However, now these are not invariants under usually symmetry transformation as we involve them, but I will want to extend them to be the invariants under quantum controlled symmetry transformation of the group G. Quantum control is very generalization what you see here. I quantumly control the shift operator or translation operator. And here we can think about having invariance under this reference frame transformation, which under which the form of the observable remains the same. We just change from C reference frame to A reference frame, and therefore also the systems change from AB into BC. But this observable, if we write it in some Hilbert-Schmidt form as a function of some generators of algebra, maybe for example position and momentum, they have the same functional form. So they indeed has the same form, they are invariant form invariant. And this transformation are now generalization, which was done in this paper, of the translation invariance in which we use any group here. And here is the unit representation of this group, which acts on B, but how it acts is quantum controlled, and that's why we have here bold quantum controlled symmetry transformation. So we can extend the notion of the symmetry, and here is one example of that. We said that under quantum translations, the states can change very much, but the observable that was a relative observable between B and E, like a relative distance between B and E, will still be a relative distance when I jump on A. The only restriction here that when I am in A, I already assume that A is in origin, so I don't have a distance here because the distance to A is 0. And for example, momentum of B is also under this transformation invariant. So we see that we can go on with extending the notion of invariance to this quantum controlled translation or quantum controlled group transformations. So does it do any job for us? Okay, we introduce some notions, and now the next what we want to think of is can it help us look at certain situations in a new view? So what you see here on the left-hand side is a situation that is probably the most simple situation one can imagine in quantum gravity or low energy quantum gravity, a type of the experiments that we hope maybe in 10 years time from now or maybe shorter we can manage to do. Of course, we make a Gedanken experiment and we make a cartoon of that. So what you have is, of course, not Earth in superposition, but some massive object, a nanomechanical oscillator or dielectric spheres that are put in a superposition at 2 positions. And then we have some quantum mechanical system and we have some reference frame. So now I have changed a little bit notation, but I will now establish the connection so that you can follow and connect with the previous slides. R is this initial reference frame that was in our previous slides C. then we have a B, which is a system, quantum mechanical system, and then we have A, that will be the new reference frame on which I want to jump. Now, what you see on the left-hand side is a situation where there is no, at least no consensus among physicists what we expect in these experiments to be true. Why? Because we have a large mass in a superposition, and this large mass in a superposition will produce some kind of superposition of gravitational fields. And then there are many approaches how we can deal with this, none of which are equivalent, that maybe we still should use linear quantum mechanics and do some kind of low energy limit of quantum gravity, or maybe superposition will break down because we don't believe that massive objects can stay in this superposition and so on. So what I want to say is that at this moment, I will be ignorant about this left-hand picture. What you see on the right-hand side is a change of the reference frame. So the same physical situation is seen from the reference frame when I jump on the mass. So that's why the mass is localized here, but everything else with relative to mass is delocalized. Now this situation here is something more benign, something which we know how to deal with, depending on the exact level of exactness we want to deal with. But in a worst case, so to say, the most complicated case, this will be some quantum mechanics or quantum field theory on the curved spacetime, where the spacetime is a well-defined state produced by this mass. Now, our transformation S transformed this situation into that transformation. And also, it tells that if on the left-hand side, we have the usual Hamiltonian of the situation, where I assume that the mass of the large object is very large, such that it doesn't contribute kinematically. So I have the system, which is a reference frame, the systems which has a kinetic part, and I also have potential produced by the mass for this small mass, and R is far away such that that doesn't really interact with the rest. Then if this is the Hamiltonian that we are used, then the Hamiltonian in the previous one, previous situation, which we are not sure how it should work, has this form, which is form invariant, namely Hamiltonians is invariant in quantum control translations, and we can also think that then the dynamical laws have the same form in both reference frames. So we have the invariance of the dynamical law under now not only classical but quantum reference frame, or maybe quantum coordinates transformation if we extend this to the field theoretical picture. And this can help us to face the following situation. Let's say, and as I said, we will be ignorant about this situation, that we don't know how this test particle S moves in this strange non-classical spacetime. But then we do believe that the symmetry is extended to quantum symmetries and then move into reference frame in which the mass is localized, and then solve the problem here because we know how to solve this problem. And then depending, as again, how exact you want to solve this problem, but in some semi-classical limit, you can think about each of these possible amplitudes following geodesics. Here in the picture 3, the old reference frame is not drawn, is not pictured. So each of these amplitudes or possible positions of the proparticle will fall towards the gravitational field through the geodesics. And then you can go back in your previous and original reference frame and see, okay, if I have actually mass in a superposition, this particle will then fall into the superposition of these geodesics, and you have some kind of a commutation diagram here that you can maybe justify going this way along path, but once you justify this, you can go also directly from 1 to 4. This methodological loop is not only applicable on these structures and Newtonian situation in which time, for example, flows absolutely at absolute rate, but it can also include some post-Newtonian effects like time dilation or gravitational time dilation. So I will not put any calculation, but the idea again is the same, except that in the middle or wherever it's placed for the Pro particle in the previous case, now we have a clock. We have a system that ticks a certain rate, and we might again ask ourselves, well, what's the tick rate of this clock if it is in a superposition of two gravitational fields? And so what we do then, we go back again into the suitable reference frame in which the space-time is well-defined and gravitational field is well-defined. We have then two possible amplitudes of the clock. And then what we do is with this clock is that we know what is happening. This is a usual time dilation. That clock that is placed closer to a source of gravity will tick slower, and that's this orange line, as compared to the clock that is further away, which ticks in a higher rate with respect to the previous one. Of course, we are not talking here about two clocks. It's a single clock at two positions, but we know, and we did do already these experiments now, even at the distance of 1 centimeter and less in gravitational field of Earth in our laboratories. So there is a difference in this ticking rate depending on where the clock is. And then we can go back in the original reference frame and think about this clock not being in a fixed gravitational field, but rather that the Earth itself, or whatever the object of gravitation is in a superposition, and the clock then ticks in the superposition of two different ticking rates. And again, we can replace then, once we convince in the validity of that, this loop into the direct connection between 1 and 4. And I want now to complete this part of my talk and move to something else with a bigger picture, and not only to provide a possibility, so to say, to solve the problems on which we don't have agreement under the assumption that this extended symmetry principle is valid, but rather to compare competing models of what will happen in such an experiment. So what you see on the right-hand side is a semi-classical situation. In the middle is a collapse model, and the left is something which do obey this symmetry principle. Now, what I want here to present is a situation that you can think about in a following way. Imagine that you have an object, a massive object in superposition of these two positions, and furthermore, this object is in a trap. So we can think that there are two traps here on some distance, and this large object is either trapped in the left trap or in the right trap, but at no point these objects will change their relative positions because they are trapped. So you can think about maybe massive particles in some trap, of magnetic trap, or maybe if they have additional magnetic properties. Details I don't give, but you can think, of course, that it's possible, and after all, we do in our experiments towards this macroscopic superposition trapping the particles. And then in addition to this massive particle, there is a pro-particle. Now, there are these two lines, the horizontal lines, the upper and the lower part. These two lines are actually connected by the quantum reference frame transformation. So we can think about this as a laboratory frame, maybe the upper one, and that this is the frame when we jump, so to say, on the massive object. Now, semi-classical gravity is a gravity in which you assume that the source of the gravity is sourced by the average value of the gravitational field. So let's assume here that the only gravitational field comes from the very massive object, because the small pro-particle does not backreact. And let's talk about first the lower picture. In the lower picture, the gravitational field is sourced by this large mass, which is, however, localized. So this is really like spherical, symmetrically gravitational field. And in that reference frame, a small pro-particle is in a superposition of these two positions, and naturally will be then attracted, each of them, these amplitudes, to move towards the source of the gravity. So really, we have a situation in which this mass in a superposition will fall towards the large mass. In the upper picture, however, if we place this pro-particle in exactly in the middle of this large mass that is trapped and cannot move, this small mass will not move, because exactly in the middle of between these two, the overall force in semi-classical gravity is 0. And so we see that these two situations are physically non-equivalent, telling us that in semi-classical physics does not obey this symmetry principle, namely the physics from different quantum reference frames is different. How about collapse models? In the collapse models, under the same conditions, we may start from the lower picture, and the collapse models assume that if we have a large mass in a superposition, this superposition will collapse. However, the collapse models have to explain also the possibility that small mass do not collapse. We have so many experiments with a low mass superposition. So in the collapse model, in the lower picture, when the large mass is localized, the small mass has not enough mass to collapse spontaneously. So we will have the same situation as before. The small mass will go towards the large mass. However, in this other situation, where the large mass appears to be non-local or superposed, the collapse model will kick in, and with 1/2 of probability, we will collapse this superposition on the right-hand side, in which case the small mass will move towards the right, or to the left, and the small mass will move towards the left. In that case, we see that, again, the physics is different in the two reference frames, depending in which reference frame we are, and therefore also collapse models are not symmetric under this extended quantum symmetry. On the left-hand side is something which many, I think, lower energy limit of quantum gravity theories should be compatible with. And that's the situations that no matter which reference frame we see, we will have the same situations, namely that either the large mass is in a superposition, large mass in superposition, moving towards the small mass, or the large mass is in the center and the small mass is moving towards it. So there is no difference in, these are just different perspectives of the same physical situation. Okay, now I'm moving towards a little bit something different. When I introduce these invariant observables on the quantum reference frame transformation, I already mentioned that, for example, the relative distance, which were invariant on the classical reference frame, is also invariant on the quantum reference frame. So one may think that this is always the case, and that if an observable is invariant on the classical reference frame, then it is invariant also on the quantum reference frame, branch by branch. And well, I may pose here a question, is this always the case? And I want to show you an example of something which is doesn't remain invariant, although in quantum reference frame transformations, although it is invariant at the classical reference frame transformation. So I move to something different. The transformations will be the same, but the subject of our interest is somewhat different. Let's talk about not one copy of the system, but let's talk about many copies. Why many copies? Because I want to think about some properties of many copies of the quantum state, like coherence or entanglement Of course, I can assign this to single copy systems. I mean, there are properties of the single copies, but if we want really to measure entanglement or to measure coherence, we will need to make a tomography or use many copies. That's why I'm saying here n copies. Now, when we move from one classical reference frame to another classical reference frame, and this is a situation which is analog when A and C are very, very localized, then we know that by changing the reference frame, the coherence and entanglement will not change. So first of all, here I talk about coherence, and coherence is always basis dependent. I talk about coherence with respect to the basis G, which is G is the basis of representation of the group of transformation, yeah, X in the case of translations. And coherence is something which is, there are many measures, but one of them is the difference in von Neumann entropy, that's here a von Neumann entropy, between density matrix that is diagonalized, that's the diagonal form, and the original density matrix. Yeah? And whereas the entanglement is something which we can also express through the Shannon entropy of the reduced density matrix between A and B. And each of these properties are invariant under classical reference frames. And that's why we can move our apparatus or we can move ourselves and perform this measurement, and this will not influence the level or degree or measure of coherence or entanglement. However, when I introduce the quantum reference frames, you could have seen that something very strange happened, because we had this situation in which at the beginning, for example, we have two systems, A and B, which were factorized. A was in a superposition, B was maybe localized, but in any case, that was a product state. But once we moved to another reference frame, C and B became entangled. So that's very strange, because it seems like I can create resources, like a coherence and entanglement are resources for quantum information, just by changing my view. And indeed, this can be quantified, what I said, by the statement that coherence and entanglement, each individually, are not invariant on the quantum reference frames. This is the picture, but you can also compute it using the same measures, for example, through the von Neumann entropy, either of coherence or von Neumann entropy of the reduced density matrix of entangled pair, that these things do not preserve the value when we move from C to A reference frame. Now the question is there any other property that would be invariant on the quantum reference frames? And surprisingly, we show in this recent paper that was published in PRL that the mere sum of these two measures is invariant on the quantum reference frame transformations. So what we showed that, yeah, well, maybe in this initial picture, you have everything in the coherence of A and nothing in the entanglement, but that what you have in coherence in entanglement, in coherence in a single particle A will be transformed into entanglement between C and B, now with no much coherence. So what it turns out, and these are just extreme cases, that also intermediate cases are like that, that whenever I have coherence plus entanglement with respect to one reference frame, it is the same as the sum of the coherence and entanglement in another reference frame. This is not the only measure that is preserved. You can somehow also adapt your coherence entanglement to be more sensitive to the squares of the density matrix elements. So you can think about something L2 measure of coherence, or linear entropy as the measure of entanglement, and then again you will have invariance of the sum. However, if you start to combine something from quadratic measures with logarithmic measures, this is not in general true. I might actually skip the proof, but you are happy. I'm happy to go back if somebody is interested. The proof is very simple. And now we can ask ourselves, okay, yeah, well, we already showed that the sum is not invariant under any pair of quantifiers. And this shows a little bit for people somehow uncomfortable situation, because sometimes the sum is invariant. Sometimes if we choose a different measures of entanglement and coherence, the sum is not invariant. But I think that this is actually a very deep message. And I want to compare this situation with a situation that was at the very beginning of my talk, that if you think about Euclidean spatial translation, then the relative distance, but also any function of the relative distance, is invariant. But when we go from the Euclidean to the Lorentz symmetry, we cannot combine just any measure for the spatial translation and temporal translation and hope that this will be invariant under Lorentz transformation. A very specific form where we have a distance squared and then minus distance squared of the temporal and spatial distance give rise to invariant property under Lorentz symmetry. And that's similar here. The quantifiers that yield the invariant observable in the sum reflect the symmetry of the problem. So I think that it's something very deep in the fact that only some measures in the sum give invariance under quantum reference frame transformations. Okay, and now I'm coming to the last part of my talk, and I want to allow also some time maybe for questions, is, well, but still, that's very nice. We see that there is a sum between coherence and entanglement that is invariant. But from the quantum information point of view, we can still feel a little bit uncomfortable by the mere fact that, for example, entanglement alone can be increased or decreased by mere change of our view from one to another quantum reference frames. And how is it possible? And if it is possible, can we make use of it and generate entanglement again and again in some kind of perpetuum mobile fashion? And here is the reason why we can't do that. So what I here present is some situation from the point of view maybe of a laboratory, which is an original quantum reference frame A. And so, sorry, this is C, should be C. I'm sorry, here, C, you see this is in respect to the C. So in that point, from that point of view, you see a Bellin experiment in the usual sense. What we have is entangled state. Then we have some choice of maybe local settings to perform the Bellin experiment, and then we get some result. And well, that's a usual Clauser-Hahn-Shimoni-Holt situation in which we start with a maximal entangled state, and the set of unitaries that is prepared by Alice or Bob is given by this certain set of unitaries. And of course, we will get violation of Bell inequalities. Now, when we move from the C reference frame to A reference frame, so it should be here A, what we do is we apply certain set of transformations that move from one to another reference frame, which in terms of the circuit means that we insert certain unitary transformation. Of course, these unitary transformations are such that overall probabilities will not change. That's just unitary transformation applied both on the measurement and transformations and the state. So the Born rule or transition probabilities will never change with this, but it will change how the state look like or transformations look like or measurement. It turns out that if we apply this now for the spin, and I didn't fully introduce the transformation for the spin, but they are very similar fashion like transformations for the translations, will turn out that we can find some reference frame transformation in which the state at the beginning will be factorized and also the results will be factorized, but then the set of local operation will not anymore be local transformations. So it will be non-local transformation, meaning that even if Alice changed the setting on her side, she will also influence the state on Bob's side. And if that's so, that should suggest that by quantum reference frame transformation, what we do, we actually change the state non-locality in some observable non-locality, such that you have to pay somewhere these resources. Namely, maybe from going from the right to the left-hand side, you can, by mere change of your view from one quantum reference frame to another, produce entanglement, but that will also be a cost that here, in order to violate Bell inequalities, you will have to use non-local operations, so non-local observables, where on the left-hand side, these were local observables. So some type of non-locality has to be paid on both sides, and there is no free lunch. However, in both cases, you can show that both scenarios are incompatible with local causal condition imposed by John Bell. And therefore, the question is only whether you, for this incompatibility, you will need to pay into non-locality of your state or non-locality of your operations. And with this, I want slowly to conclude. I talk about observables that are invariant under quantum reference frame transformation. I gave two examples, one with Hamiltonians and one which is about coherence added to entanglement for certain measures. It would be very interesting to find out which other single copy observables may have this feature. I also provide the way why I think this is interesting is just because, as in any reference frame, the advantage is that in some reference frame, physics may help us solve the problem, and that help us to predict the dynamics of falling pro-particle and time dilation in presence of gravitational source in superposition. And although these things is going beyond perturbation regime, because we can have very, very different states in one or the other amplitude, we are still restricted to something which we call superposition of semi-classical states, meaning that each amplitude in the source of superposition is very classical-like state. And of course, we have superposition of that, but it will be necessary to go beyond that to give a more complete picture of quantum gravity experiments that we expect in future. And with this, I would like to thank you for your attention. I'm happy to answer questions if there are any. I'm not hearing anything, so not sure. I don't hear well. It's very suppressed.
Hello, can you hear
Yes.
me?
Yeah, I can hear you now. Yeah, thank you. Yeah.
Actually, we would just like to understand a bit more the difference between a classical reference frame and quantum reference frame. So is quantum reference frame with respect to some standard state, quantum state? What exactly is the difference? It is not very clear yet, although you explained quite a bit. So when you say quantum reference, so like classical reference, for two reference frame will be say related with.
So the question is, what is the difference between quantum and classical reference frame? Was this the question?
Yes, yes. What exactly is that?
So, I mean, when we talk about classical reference frame, they're almost never explicitly in our calculation or our description. They are just implicitly. When we say, for example, the position of a particle is 3 meters, we don't say much, of course, but implicitly, that means that there is other system relative to which we measure the distance. And since these reference frames are there, even when we talk about classical reference frame and quantum particles, they are certainly there, but they do not back-react, they do not interact, they do not have classical features, and therefore, for the dynamics of quantum systems, we don't need to take quantum systems or objects, we don't need to explicitly introduce reference frame at all. But once you can think about, when we think about small reference frames that after all will obey or will be visibly obeying quantum laws. We do believe that all systems obey quantum laws, but when they will be visibly obeying quantum laws, then they will enter the dynamics and they will then interact with the systems as any other system. And then we will need to talk about them being in a quantum state, or being systems and reference frame being all in the quantum state. And then these effects of superposition or entanglement of quantum reference frame will be relevant.
Okay.
I don't know
So
whether
is there
this...
also a notion of, say, I mean, just like we have inertial and non-inertial reference frame, is there some similar notion here?
I mean, you can have quantum inertial system and quantum non-inertial systems. Inertiality or non-inertiality is something which you apply independently of the physics in which you are. So you can have, think about a classical system in an inertial system, and a classical system in a non-inertial system, or quantum system. So it's not about the feature of moving or non-moving of quantum reference, of reference frame, or moving under acceleration, or moving under uniform velocity. It's about a nature of the physics we apply to quantum to reference frame. If we are in the full quantum framework, the claim that I wanted to make, you will need to introduce a quantum reference frame at some point. But then they can be very many. Like you can have a quantum reference frame which is moving in superposition of accelerations. So then any system seen from some quantum reference frame will be certainly non-inertial, but not only that it will be non-inertial, it will have a very strange features, because we observe this quantum reference frame in a superposition of acceleration. So it's extending the notion that we have for classical reference frame, be this non-inertial or inertial, to the quantum case. One of the other example that I did not have time to introduce is, for example, the notion of the equivalence principle. So one way to introduce Einstein equivalence principle would be, well, if you're in an elevator and you freely fall in a gravitational field, then locally, in a small region in your elevator, all physical experiments will be as if you are in inertial system. And you can even think that this is the definition of inertial system. Now, what quantum and reference frame mean is that imagine you are in an elevator, and now it's a real Gedanken experiment. I intentionally make it that it looks even funny, if you want, that the source of gravitational field, like an Earth, is in a superposition, being where it is, or maybe being shifted by some distance. Now, if you're in the elevator, the quantum reference frame transformation will tell you that you will still be feeling as you are in an inertial system. It doesn't matter whether you are in a superposition of gravitational fields or you're in just in one gravitational field, the transformation of, towards a reference frame attached to the elevator will tell you that you still have inertial physics inside an elevator. So in the sense, you can take any situation from the classical reference frame situation and then make it quantum. But that's a very useful notion, because if you believe in this principle that I said and believe in this transformation, that will tell you that the physics in a small region, even if you are in a superposition of gravitational field, if you're in a freely falling elevator in this small region, you will not see any difference. So Einstein equivalence principle will be extended to these systems. It was a more extended answer to your question. I hope I could bring it closer. I again have a little bit problem with your voice is suppressed.
Thanks for the nice talk. Actually, you mentioned that Bell violation is kind of invariant under this quantum reference frame transformation, right? But
Yes.
let's say entanglement measure, for example, is not invariant.
Yes.
So is it that then, I mean, in case of Bell, we calculate, let's say, correlations. Is it that the correlation takes care of the invariance, or is anything deep physics inside it?
Well, can you repeat the last question? Is it the correlations?
The correlation takes care of the invariance of the, Bell violation. So what's the physics behind this?
Yeah. So when I say that, okay, so one way to, if you measure correlations and you say out of the correlation, this is things that I can observe in the laboratory, it seems like I'm saying a contradiction, because on one hand, I said that measured results will not change from making one experiment in one quantum reference frame to another. And then I said at the same time that entanglement can change as a measure. So you may wonder why this is not contradictory, because entanglement measures are based on correlation measurements. And so how can it be that entanglement measure is changed, but measured results are not changed? Well, this comes from the fact what you measure. In original reference frame, you take these two particles, let's say, in a tangled state, and you can measure, for example, correlations by measuring Alice having a local measurement, a Bob local measurement, and then they compare the results, they repeat many different settings, and they construct the entanglement measured. Now, what in this other quantum reference frame transformation will be is that this quantum reference frame transformation will change both the state and your measurement observables in such a way that the Born rule, that the probabilities are always the same. So that's the statement that probabilities are always the same. But what will you measure and on which state you will measure, that will change. So you start with entangled state. After a quantum reference frame transformation, you might even get a product state. So entanglement has changed from non-zero or maximal to zero. However, you will also change the measured observables. So those that were product will now be entangling measurement. So in that sense, the state itself will change from the entangled to product state. But because the observables will change at the same time, the measured probabilities on that state for that observable will remain the same. So you will not measure usual correlations. Yeah.
Okay, so this is question. Yes, okay. If the sum of there is another question.
Thank you for the nice talk, Professor.
Thank you.
You mentioned the sum of entanglement and coherences are invariant in quantum reference frames. So, is there any trade-off between the coherences and entanglement?
Yes, there is a trade-off. You can have a situation in which one is maximal 1 and the others is 0. You can start with this, and then you see that the sum will maximally be equal to the maximal value of any of them. So if you start with entanglement 1 and coherence 0, they cannot go beyond 1. So when you change from one reference frame to another, there is a trade-off, and you can just push this one towards maybe the one that was not, that was 0. So this one will be then partially encoded in the entanglement or coherence, or only in coherence, but nothing in entanglement, or the other way around. So you have this trade-off. And I should also tell you that this trade-off is actually true for any measure. For any reasonable measures of coherence entanglement, we show this trade-off. The interesting thing is meaning trade-off in a sense of inequality. So the sum of entanglement plus coherence is less or equal than some bound, such that you will all have as a trade-off. The interesting thing with the fact of using the von Neumann-based entropy, or these quadratic-based entropies, that the sum will be even constant. So the sum will not be less or equal than trade-off, that bound, but it will equal to one particular value.
So anything beyond 1 and 0, then there is a trade-off, or if one is 1, other is 0 only, then it is fixed or something?
No,
The sum is
so
same. It didn't matter
yeah, the
one
sum
to
is the same, yeah.
It is 0.5 to start with.
We are here talking always about pure states. So I'm not sure whether there is always for any value in between. I mean, of course, if you would have. So I think this will maximize things. So I do think that it's always smaller than 1. Yeah.
No, but what about if you have multi-parted situation? You have the 3 parties.
That's an open question. That's a very nice question, and it's very interesting whether one can extend this to 3 parties. And also, I mean, of course, then it's very many different measures of information. Measures of entanglement, bipartitive, 3-partitive. That's completely open. We don't know anything about that.
More questions? Okay, so I mean, I think let's thank our speaker for educating us about a very new development in this area. So let's thank our sir.
You already had a talk on quantum reference frames, are you saying, or?
No, so we are learning something new, right?
Yes, I was not, I mean, my interest in the recent years shift towards some kind of intersection of space-time physics and quantum physics, which is relatively small field of research still. And we are also learning a lot of things. And the colleagues of us who are not trained in quantum information are learning things from us. So it's exciting field, but it's a little bit at the border of the traditional quantum information subject.
Okay, then thank you.
Thank you.